All right, so let's continue looking at the lab before we move on to the why things dissolve and why things mix together. So we ended up yesterday talking about the polarity of iodine and the polarity of sodium chloride in backwards. And so let's take a look at the solubility data for the sodium chloride and for the iodine. So sodium chloride, I have these four vials right here. And left to right, we see NaCl in water, ethylene glycol, hexane, cyclohexane, and ethanol. And you should be able to see, where's my pen? So you should be able to see that with the water, there's nothing on the bottom of the vial. So the water is completely, oh, what the heck happened there? Completely soluble. Let's try to go back and see if that's going to fix it. Nope, that's not fixing it. All right, so look at your own. Let's see, maybe cancel. Yeah, okay. There we go. That's better. All right, I guess I can't draw on it like I did before. All right, with the ethylene glycol, you can see there's a slight amount of sodium chloride on the bottom. With the hexane and the cyclohexane, all the sodium chloride is still there, so that's completely insoluble. And with the ethanol, the same thing. The sodium chloride is insoluble in the ethanol. So let's go back and put that in. We saw that with the sodium chloride, we had, oh, I guess it helps if I pick my pen. We had soluble in the water. Let's call it slightly soluble. Now we're going to get to degrees of solubility. Slightly soluble in the ethylene glycol, insoluble and insoluble in the hexane, and in the ethanol, it was also insoluble. So we have the data now. If we scroll back down to that, you are going to have to answer number 2. That's going to be part of what you have to answer. Which is more soluble, water, ethylene glycol. Does this fit the hypothesis that two substances will be polar if they have similar polarities? Now let's go look at iodine. So first, if you make the prediction, hopefully you should understand the prediction that iodine should be most soluble in the nonpolar thing. So cyclohexane and hexane, and the least soluble would be in water. I want you to explain why that is. Actually, that's this whole thing here. So explain why that is. Now, let me just take a little aside here. I usually stop at this point and do a little aside. Oh, no, I'm sorry. The aside comes after we look at the results. So let's go look at the results. And this is pretty cool. So let's start with the hexane and the cyclohexane, vials 3 and 4. You can see this pretty purple color. Now, if you remember back to the elements lab, we had iodine was element number 1, and I did a little demonstration where we played a little Jimi Hendrix, some purple haze, and we saw that the iodine vapor was this pretty violet color. Well, every time iodine molecules, the I2 molecules, are separated from each other, they form this pretty purple color. Now, other things happen in other solutions or other solvents. If we come down to the ethanol, you'll see this kind of brownish yellow, dark brown, yellowish kind of, a dark yellow kind of solution. And what's happening here is the iodine is dissolving. It's dissolving in a slightly different way. This is actually called a tincture of iodine. And if you've ever had to give blood or had your blood taken and the nurse swabs your arm with that gooey yellow substance that dries and feels kind of sticky, that's exactly what it was. Iodine is actually a disinfectant. And so that's what you'd be getting on your arm to prevent infection when they stick you with a needle. Coming down to ethylene glycol, you can see some of the iodine sitting on the bottom here, and it's a much lighter yellow color. And in the water, you can see the iodine, those kind of dark black crystals sitting on the bottom, and a very, very, very light color of brown. So let's go back to our data chart and scroll up here. By the way, don't forget to put iodine on your, let's put it in there now, just in case you have forgotten, onto your number line. And so in the water, we saw that it was very slightly soluble. So almost no solubility. Ethylene glycol, there was a slight solubility. Hexane and cyclohexane, those were both soluble. And in the ethanol, it was, let's also say soluble in the ethanol. Now, just an aside, iodine is like oxygen in that they're both nonpolar. But oxygen, O2, does dissolve in water. If it didn't, then fish and aquatic life, other than like dolphins and whales, they would have no way of breathing. And so this slight amount of water, or slight amount of oxygen that dissolves in water, is responsible for the life to be able to exist in the water. And the way that it dissolves in water is through a slightly different kind of interaction. Since we have a dipole with the water, and we have an induced dipole, that's that London dispersion force. So the dipole, the permanent dipole in water, can induce the dipole in oxygen. It can also induce the dipole in iodine, but it's a very small dipole, and that's why it's very small solubility. And then coming down to number 5, does this hypothesis fit the data results? Yes or no? And again, you're going to explain. And so I've circled 2, 3, and 4. Please make sure that you fill those in before turning in the lab. So now what I want to turn my attention to is why. Why does all of this happen? And I have handed out for you this document, discussion of the dissolving on a molecular level. What's going on when molecules interact with each other, different kinds of molecules? And we're going to start with, why does ionic compound like sodium chloride dissolve in a polar liquid? Now, before mixing, so I've got the before and the after pictures here. Before mixing, we have strong ionic bonds. That crystal lattice that has a very strong lattice energy holding the crystal together. In addition, there's another aspect to it, and that's that the crystal is highly ordered. As we saw in, or hopefully you will have seen in the solids video, the properties of solids, we have this ordered crystal, and the sodium chloride is being held together. Now, when you put it together with water, the water actually is going to attack the crystal, and here's how that happens. So the hydrogen atom on the water has a partial positive charge. I've got that partial positive charge written in here. That positive charge is attracted to the chlorine ions, the chloride ions, and if you get enough of them together, so it's going to be attracted to the chloride ion, and this is called an ion dipole attraction. So now we have another kind of attraction that's different from just a straightforward dipole or hydrogen bonding. And what happens is it pulls it out if you have enough water molecules attacking that chloride. Likewise, the delta minus on the oxygen, let's change colors so you can see the difference. The delta minus on the oxygen is attracted to the positive on the sodium. By the way, this is a stronger attraction because it's a full charge. So this is actually a stronger attraction than a dipole-dipole attraction. And again, we get enough water molecules around, and what happens is the water molecules gang up, multiple water molecules per ion, and what happens is it breaks the ionic bonds. There's enough energy now to break the ionic bonds, and it pulls the ions out of the crystal. And we end up with 6 water molecules around each ion. Now, I know you don't see 6 here because there's one in front, one in back, and likewise there should be some more water molecules here. But these hydration spheres is what they're called. Hydration just means water around it. Is how these ions actually exist in solution, and this is what keeps them dissolved and not forming back into their crystal. So I mentioned the order of the crystal. The crystals are highly ordered. So if this is ordered, this is more disordered because those ions are actually floating around in a kind of non-repeating pattern. And so this becomes more disordered, which we call in science, we call this an increase in entropy. So entropy is a reason, in addition to energy changes, why processes happen. And nature favors an increase in entropy and an increase in disorder. I usually like to talk about this in terms of messiness, although that's not exactly what it is, but it's sort of like what happens when, suppose you have a nice neat pile of things on your desk and you come in and you kind of scatter them around to make room to work. That scattering is a natural way of doing things, and it comes about, it helps things happen. So it's helping us mix. And anytime we mix, with one exception, and we'll talk about that one exception when we get to the unit on entropy, any mixing is going to increase disorder. So that's the reason why nonpolar substances mix. So nonpolar substances start off with no attractions, basically. Let's say no strong attractions. There are very weak attractions, dispersion forces, but there's no strong attractions between either substance. So we've got 2 substances, the squares and the circles. They're both nonpolar molecules. The nonpolar molecules have only the weak London dispersion forces holding them together. So there's nothing to keep them from moving within each other. So what happens is the substances also have thermal energy. That's at temperature. Thermal energy. And so what happens is they move randomly. This movement because of the energy. So the particles are moving all over the place. They're moving in different directions. And by thinking about just random movement, what can happen is the random movement causes scrambling. So the particles are scrambling around and they mix. Now they mix, there's nothing that's going to keep them apart because there's no strong attractions one way or the other. We're going to see that that's different on the next page. The weak interactions are not enough to exclude either substance. And since there's no exclusion, then we're going to get that increase in entropy, so more disordered and higher entropy. Next, that's 2 nonpolar substances. So far we looked at ionic, we've looked at 2 nonpolar substances. Let's look at a polar substance and water, or 2 polar substances. So this could be water and some polar substance. It could be 2 other polar materials. in polar materials, there's strong attractions between all polar particles. We've got those partial charges. So we've got our square, we got our rectangles, and we've got our ovals. So instead of squares and circles, we now have that shape. And the positive and negative charges are going to attract each other. So the negative and positive here and here, but we also have negative and positive here and here. So we've got attractions all around. Particles of each type are attracted to particles of the other type. So this attraction allows them to move within each other. As in number 2, the energy in the particles causes random movement. So let's change colors so you can see that random movement. So we got some random movement going on here, moving around in different directions. And as those particles move, they start to scramble as before. So the system scrambles, it becomes more disordered with higher entropy. And this can happen, so the mixing happens because we now have positive and negative charges attracting each other. All those positives and negatives attract each other. And these two particles are attracted to each other in such a way that mixing can happen. So now let's take a look at why a polar and a nonpolar substance don't mix. So this is like oil and water. So normally at this point, I would take and shake up for you a jar that has 2 liquids, oil and water. You can do this yourself at home. If you get some salad dressing, you shake it up. And what happens is, as you shake it up, you're putting energy into it. And before you shake it, all the polar molecules exhibit strong dipole-dipole attractions to each other. And remember from the other day, we called attractions to each other, we called these cohesive forces. So the polar molecules are sticking together. They have those strong positive and negatives there that want to keep everything together. Okay, meanwhile, there's only very weak dispersion forces between the nonpolar and polar molecules. This was like the water and iodine, like the water and oxygen example that I gave earlier in this video. Now, when you shake it up, initially the droplets of each liquid will disperse through each other. These droplets disperse through each other because we have higher entropy. Higher entropy because there was energy added. So when you add energy, you can make things do something that they're not favored to do. But then what happens is the liquids separate. So let's draw a little diagram down here. Suppose we have our delta plus, delta minus, and we have some of those, it should be a rectangle, not a square, and we have some of those rectangles that are getting in the way of things. So this would be after shaking. Initially, we're going to get something that looks like this, with the particles not next to things that aren't attracted to each other. So while we're looking at it, what's going to happen is the water molecules are going to find each other, or the polar molecules. The polar molecules are going to find each other, and they're going to separate out. They're going to go back to that picture. And they're going to separate out because they're more attracted to themselves. Again, that's the cohesive force. Then to the nonpolar molecules, that would be an adhesive force. So cohesive is greater than adhesive. And when you have cohesive greater than adhesive, you're going to separate like this. Now, be very careful. The polar molecules are attracted to the nonpolar molecules through dispersion forces. But here's the key. the dipole-induced dipole, these are dipole-dipole. The dipole-dipole attractions, and in water it's strong hydrogen bonding, are strong enough to overcome the tendency to higher entropy. So we're actually overcoming the desire of nature to move forward because of those strong dipole-dipole attractions. All right. If you have any questions, let me know. For the unknown. So let's go back to the lab for a moment, and we'll finish this up by thinking about the lab. So in the lab, we have some unknowns, and you should be filling in the solubility data for the unknown. And from the solubility data, you can then match what you have as solubility for what you think might be your unknowns. Now, be careful. Let's go look at pictures of the unknowns. You have this document as well. So here are the 5 unknowns. You can see, let's zoom out so we can see them all at once. Okay, so these are the 5 unknowns. Now, if you have one of the first 5, you're going to have to put in some delta plus, delta minus. If you have calcium chloride, then you want to draw a picture of calcium chloride that looks like this, with the 1 calcium 2 plus ion and the 2 chloride negative ions. So when you look at the lab, you're going to figure out, based on your solubility, what the polarity of your unknown is. And think about the hypothesis we had. What is this the most similar to? Do we have solubility all across the board? Do we only have slight solubility, one side or the other? And so figure out where you are. Put your unknown on your number chart. Don't forget to put the unknown on the number chart so you can make sure you get it right. And then what you're going to do is you're going to try to figure out which unknown is yours, and then you can email me. Tell me what your results are. Tell me what you think your polarity is and what you think your unknown is. Now, there's 2 that are ambiguous. Everything else should be relatively straightforward. When you've done that, I will write back and confirm what your unknown is, and then you can go through the next page here. I want you to draw in the first part of the question here. I want you to draw just a 3D structure of your molecule or your, of your ionic compound, and make sure you get the partial charges in. Also, make sure if you have a nonpolar substance, make sure you write none. So I know you didn't just forget to write in the delta plus, delta minus. Okay. So you determine the polarity of your unknown based on solubility. But now look at above. Look at the results. Look at your delta pluses, delta minuses, and this is going to be essentially what's the percentage of polar. So how polar is this molecule? And that should give you an idea of how polar it is. Is it polar or non-polar? Is it ionic? And if it is polar, if it's covalent, how polar is it? So look at the charges, either full charges for ionic or the partial charges for polar covalent molecules. Next, in number 4, you're going to draw 2 molecules of your unknown, and you're going to write in any full or partial charges and then show how those 2 molecules are attracted to each other. If you have the ionic, then draw 2 calcium 2 plus and 4 iodide, and try to make it look, so for ionic, you want to draw something that looks like a crystal. So just make it a nice, neat looking crystal. And then finally, in number 5, you want to draw water, showing how water is attracted. So you're going to look for the delta plus being attracted to delta minus on everything, and the delta minus being attracted to delta plus. And actually, let me draw those as dotted lines. If you have delta plus, delta minus. If you have ionics, delta plus being attracted to the negative, delta minus being attracted to the positive. If you have nonpolar, what I want you to draw is the nonpolar molecule. Nonpolar molecule. And then up above that, I want you to draw two water molecules attracted to each other. And that will help you to understand how this works. And finally, on the last page, there's an article you have on detergents. Please read that article and answer these 3 questions. All right, so as I was saying, if you have any questions, email me or Mrs. Rinaldi, and we will get this lab done. We will go over it on Monday in class, and then it will be due on Tuesday at 1 o'clock in the afternoon.